Okay guys and gals, I want to go ahead and show you the rest of 14.3. You may have already been working on the second part, but I want to make sure I give you some examples and go through it. Sorry it's so late. Surgery went well, but I'm going to have another surgery to fill in the big hole they took out pretty soon with the cadaver bone. So if anybody has any bones I can borrow, let me know. Okay. Alright, first thing is we need to be able to find the partial derivative when it's defined implicitly. And you'll remember that all that means is that the z is not isolated. So right here it's kind of just mixed in with the equation, so it's not by itself, it's not written explicitly. So that would be the opposite. Alright. So the way we do it is, again, you just treat the y as a constant, and then anytime you come across the z, then you're just going to write the partial derivative of z with respect to x. I'm going to find the partial derivative of z just with respect to x. I'm just going to do that first one, and then obviously the one with respect to y is the same thing, same idea. So first part, of course, that's 3x squared, and then that would be 0 because y is a constant. This would be 3y squared, and then again we have the chain rule there, dz dx. Well, we should say partial derivative of z with respect to x, just like before with our single variable calculus. Before, whenever we would come across a y, we would say dy dx. So now we come across the z, and we would say dz dx. Okay. This part here, we have to think of it as the product rule because it depends on how you want to split it up, but I split it up as 6y as one function and then z as its own separate function. And so you have to do the product rule. So I did derivative of the first function would be 6y, because it would be the 6 and the y would be like the constant in front of the x. And then times the z, so that's what I have here, plus, and then I would find the derivative of the partial derivative of the z. This thing's acting funny. So I would have partial derivative of z with respect to x, and then I would just write that as it is, 6xy. And then really from there you just want to isolate your partial derivative of z with respect to x. And so again, similar to our single variable calculus, you just want to get all the dz dx's on one side, and then factor it out, and then isolate it. So pretty straightforward from there. Let's see. So when we have more than two variables, same deal. You just let all the other variables be the constants, other than the variable you're finding the partial derivative with respect to. So, like this one here, example 5, we have this particular function. So if I was going to find the partial derivative with respect to x, then I would just treat the natural log of z, of course, as a constant. I would rewrite this, e raised to the xy, and then the derivative of the inside, which would just be times the y. Chain rule. And then partial derivative with respect to y, similar deal, the natural log of z would come out in front, it's just a constant. Rewrite the e raised to the xy, and then if the y is the variable, then the x would be that number right in front, so that would just come right out in front. Or I'd multiply by x. And then the z, what we would do there, if it was partial derivative with respect to z, we'd treat the e raised to the xy as all as a constant, so that we'd carry that along for the ride. And then the derivative of natural log is 1 over whatever is in that spot, so that's why it would be 1 over z. So we could rewrite it like this. Alright. Example, just kidding. So sometimes we can do more partial derivatives. So you just do them. You do the first one, then you do the second one, and then the notation is like this. So partial derivative with respect to x, and then with respect to x again, etc. So these are second partial derivatives. And this is the notation for second derivatives. So you can pause it if you want to jot down all the different ways. This 2 here, similar to single variable calculus, just shows that you're finding the second derivative with respect to x, twice. All right, all that seemed to make sense. All right. All right, so same thing there. Just the order, you have to do the x first and then the y. Oh, I don't want the keyboard. No. Okay. All right. All right, so let's do this one. So find all the second partial derivatives. So that's just kind of a big mama problem because they're asking for every single possibility of second partial derivatives. So first, of course, you need to find the first partial derivatives. So you guys know how to do that. So we did that in class the other day. And then that's the partial derivative with respect to x twice, partial derivative with respect to y twice. And then the other possibilities are the xy and the yx. So I don't think I'll run through all the steps there, but you can check, verify that those seem to be done correctly. What's interesting about this is that the partial derivative with respect to x and then y is the same as the partial derivative with respect to y and then with respect to x. So not necessarily coincidence, that tends to be the case. Okay. And there's actually a theorem about that. And that is this dude here. He discovered that is the case a lot of the times for most functions. Okay. All right. He says that happens whenever both of the partial derivatives are continuous on that particular domain. Then that will be the case, that they'll end up being the same. Okay? So you'd have to look back and see that those, the answers that you get, that those are actually continuous on the whole domain, which we'll have to go back and look at that continuous business. Okay. Now, let's look at, and then this is no different. This one just took me a billion years to write. But all you do is just do it right in order, just the way it's written, the notation. So it's not hard, you just have to obviously pay attention to details. So here's the first one, obviously cosine of that amount times the 3, because that's the 3 that's in front of the x. And then you take that answer and you find the derivative with respect to x again. So you would have your negative, you carry your 3 along for the ride, but then it's a negative because it's cosine. So negative sine of that same amount, and then you'd have to multiply by the 3 again because it's with respect to x. And then I would clean it up a little bit before you try to find the next partial derivative, so I box that. And then with respect to y this time, so we carry along the negative 9 for the ride, and it's cosine of that same amount. And then this time it's with respect to y. So what's in front of the y is the z, so then we'd multiply by the z. And then clean it up before you try to find the partial derivative with respect to z, because we actually need to do the product rule. Because with respect to z, we've got a function here, and then we have this whole function here. So we apply the product rule to this. So what do I have? I have negative 9. That's the derivative of this part. And then I just rewrite this as is, and then plus, and then the derivative of the second part, which is negative sine of that same amount, and then times the derivative of the inside because of the chain rule. So then times the y, and then multiply by that same amount. So negative 9z, not making any changes. Okay? And you could clean that up slightly, but not too much. All right, I think, well, the only other thing is this guy. He has a particular equation, and he says that when you find the second partial derivative of the x's. You do both the x's, and then you find the partial derivative of both the y's. That when you add them together, they equal 0, and that tends to be an equation that has some applications. So these are a few of the examples of the applications, and this is to conclude an example of how to use, or an example of how his equation makes sense, how it works. So if you had a particular function, you would find the partial derivative with respect to x, then find the partial derivative with respect to y, and then again find the partial derivative with respect to x again, and then find the partial derivative with respect to y again, and then just go ahead and add these two together and see if they definitely add up, and if they add up to equal 0. If they do, then we're showing that satisfies his equation. Excuse me. Does that make sense? So hopefully you guys will be fine to work through the problems. I would also ask that you make your level curves, or your contour maps. Make sure those things look awesome in the back of the room. So I'm going to say finish contour maps. Make sure they look amazing. And you guys are super creative, so I would love to be able to display those, but just try to make sure they're super accurate so that we're doing it right. Okay? Have a great weekend. I'll see you Monday, and we'll figure out what we want to do there, whether we want to go back and look at limits and continuity or what. But have a good weekend. All right, later.